Quick show of hands. How many of you are already using some streaming system? All right. How many of you are planning to use one? All right. So I'll tell you just a couple of words about what am I doing. I'm principal architect with strategic architecture at PayPal. That means that I'm looking over a number of projects, focusing particularly on developer experience and the tool chain that we have to build software. And that includes highly scalable systems, big data systems, a variety of very exciting projects. In my previous life, I was running my company as a consultant traveling around the world, working with clients worldwide, and was focusing on better ways to develop software through software architecture, highly scalable systems. Lately, it was a lot of Scala, functional programming, and big data systems. And one of the things that I have seen in my consulting engagements in the past is that there are particular challenges when it comes to selecting streaming systems. First of all, there is a great allure of streaming, particularly as organizations are trying to process more and more data in real time or near real time, as opposed to batch and in large increments. And often there is a misunderstanding what these streaming systems do. So one of the ways to illustrate that to newcomers is to think about streaming approach inverting the way how we think about processing data. So in conventional systems, we have a whole bunch of data. We are sending the queries, and we are getting the results. Streaming architectures are inverting this picture, and we are making the queries static. We are streaming the data, and the data is going through these queries, get transformed, and this is where we get the results. And what is interesting in the organization like this, the traditional organization of inner architecture of the system would not work because the demands are very different. And that resulted in a creation of a number of frameworks for stream processing. So if you go and look around what is available, there is a whole range of them. The question is, which one would be the best system for your application? So you need to think about different ways of organizations or decision choices that have been made in creating these streaming systems. From the point of view of developers, you may focus on developer experience. So how do we write our systems that will process streams? You can think of a fairly lightweight approach. For example, like with Akka Streams, you have a library. You bring it in your code, and that is what you use. You have now some approaches that are bringing streaming into the messaging systems, like what we see with Kafka Streaming. And then you have the group that originally started this area, and these are the big data frameworks, starting from Storm, Spark, Flink, and so on. On the other hand, these systems have also different solutions to their non-functional requirements when it comes to throughput, performance, latency, and so on. And you see basically two approaches. One approach, which is the true streaming, where you're processing one record at a time, which you see in systems like Flink, Beam, and so on. And you have another approach where we are faking the streaming by doing processing in small batches. And this is what Spark is doing with their micro-batching approach. And there are differences. Sometimes one approach is better for low latency. Sometimes the other approach may be better for higher throughput. And you need to understand the behavior of the system in order to match your requirements. When you think about what is happening inside of these streaming systems, the good place to start is with one of the oldest systems in this space, which is Apache Storm. It's an architecture that is designed purely to processing of streams, and it has spouts, which are sources of data, and it has bolts, which are the units that are doing the processing. And the data is streamed as tuples between these nodes. The interesting thing is that in order to promote scalability, all of these things are replicated, and they are actually running in distributed fashion on the cluster. The overall organization there is such that you have the master daemon process, which is receiving the code, distributing the code to workers. You have a zookeeper as the system that manages the cluster. This is the source of true information in the cluster. You have supervisors, which are daemons that listen to work. And then you have eventually the workers that are running on tasks utilizing the JVM threading. So this is a solution that is giving us very good latency. It's a system that is used in real time. Originally, the API was relatively low level, so the developer experience in working with such a system is that you need to do more work in order to get your results. But there were some improvements. There is a library called Trident that is adding higher level of abstraction. It will remind you to processing of streams like what you have in Spark or Flink. And Storm 2.0 is coming soon with a number of improvements. And you see, a system like this is completely dedicated to processing of streams. Sometimes you need a little bit more flexibility. And we have seen that in the system like Apache Spark. Apache Spark was originally designed as a system that is doing batch processing of big data. But then streaming emerged as one of the requirements. The approach that Spark is using is to take the stream of events that is coming in and package them into batches of small data. So each of these micro batches is going to be processed and will be producing some results. The internal data structure is a derivative of what is known as a resilient distributed data set. In this case, we call it discretized stream, and it represents the RDD abstraction. And you know from Spark, RDD is going to provide you with the data that is typically kept in memory, and it is distributed across the nodes in the cluster, and then we can do parallel computations on that. The beauty of that is that the programming model, the development experience, is very similar to processing batch. And in fact, if you compare the two ways of writing the code, here is the batch word count. And you can see here, we are creating a Spark context. This is a way to access the Spark. We are getting the lines from some text file. And here is the little bit of flat map, and reduced by key that will give us our word count. So this is for batch processing. If you think about streaming, notice what are the differences. And this is very cool. So notice that the main body of code is identical. What is different is now we have a streaming context, and we are defining the window, and we are defining our input, which is coming from a stream. And that can easily be networking, it can easily be Kafka, and so on. So this is one big thing that was happening in the usability of the APIs of streaming systems. Programming batch and programming streams are converging. And we see that in the systems that are coming after. One of the newer additions to this is that you have a SQL. You know, if you have a data in some application area, the next thing that will happen, somebody will demand SQL, and then they will get it. So that is quite popular. And we see actually this is a very attractive feature because in some organizations you have people who are coming from traditional data processing or data science domain, and they are often challenged when they have to work with Scala. So they really welcome availability of SQL. Similar developer experience we see in Flink. The consumability of the APIs is similar to Spark. However, the inner architecture of Flink is very different. It is actually the opposite of what Spark is doing. Spark, as we have concluded, is batch architecture, which is adapted to process streams. Here we have the other way around. Flink is a streaming architecture which fakes batching. Because what is a batch? Batch is just a stream that terminates at some point. And quite exciting things. There was a talk this morning. Very comparable. We see a bigger uptake of Flink recently among the companies. And one thing that really stands out is very good latency because it's a natively streaming architecture. And a couple of interesting things, you know, when the Flink was being designed, there were a couple of requirements, like low latency for streaming topologies, which one could not resolved by going with batch first. Resource utilization, ability to create data processing pipelines and then optimize them, something that we had in data processing with relational databases for a long time. You create an access plan, you see what are the optimal ways of accessing and processing data, and that is missing from many of the big data technologies today. Ability to iterate and maintain state in iterations is one of the really interesting features that Flink has. And one of the use cases was ability to deal with graph processing, also with mutable state. Now, what we see is that number of systems have been emerging. And one of the really interesting things that is happening here is the Apache Beam. It's the common API layer for big data, both batch and streaming processing systems. It is inspired by Google Dataflow, which has a very comprehensive, very elegant API. And the idea came that one can take the Dataflow API and provide it as the common layer for a number of batch and streaming systems, which we then use as so-called runners for the Apache Beam. The beauty for us is that we would have the common API, and we would be able to change the execution engine based on various requirements, performance, throughput, latency, and so on. Also, when we talk about selecting the framework, this Beam gives us very useful mechanisms for comparison, because it is separating what results are being calculated, where in event time, when in processing time, and how do we relate refinements of results. And I have put here a link. When you start choosing your streaming architecture, I recommend that you go there and visit and compare the features of different streaming systems. Before Beam, we had to invent this on our own. Now we have a really nice matrix of different capabilities, and also you can see what is covered by different systems. So you can see here, for example, what is being computed. You have here different functions like parallel do, group by key, flatten, and so on. And here you have a number of prominent streaming systems. Beam model, which is just the API, Google Cloud Dataflow, which is the private implementation that you could use in the Google Cloud, Flink, Spark, Apex, Gear Pump, traditional MapReduce, JStorm, which is the Storm compatible system from Alibaba in open source, and IBM, the commercial product. So this is going to give you a nice idea about what is supported in the APIs. And what is really interesting, just about a year ago, when I was dealing with this, you could see the metrics like this. There were many more empty spots, or spots that were saying no. We see great development and progress in this field over the last year or two. Sometimes you find that running this on big data infrastructure is not such a good idea. You would like to have something lighter. Answer to that is coming through Apache Kafka. Apache Kafka allows us to do streaming. And what is really cool about that solution is that in many organizations we already have Kafka. We don't need to add any special clusters in order to do the stream processing, because in Kafka, stream processing is done as a completely ordinary, normal Java application. You don't need to deploy it on a cluster. And all these things very nicely integrate in the whole Kafka ecosystem. One of the features that was recently introduced is exactly once delivery. That caused a lot of discussions on the web. You need to understand that this exactly once delivery works really well when you have the closed world assumption. That means from Kafka in the beginning, Kafka at the end, you have the full control over the input and output. Sometimes you will see that none of this out-of-the-box solutions is going to work well for your use case. And then you have Akka Streams for coming to your rescue. This is an example of one application at PayPal. This is the crawler application. You can see here we have the list of crawl jobs, gets in the database. The values from there are streamed into Kafka. Validator for URLs, go to the web and download the pages, do analysis of the pages. We have some database of URL caches, so we don't revisit the pages. And eventually, we are sending the results to Kafka. After that, it goes to Hadoop Spark for various analytics, and also the new URLs are being fed back into Kafka. That needs to run really fast on a number of machines, and Akka Streams provide us backpressure mechanism, and you will see in the next slide how that actually works. With Akka Streams, we have two great things. One is we have a DSL that can very nicely represent our pipeline of processing. So this is the actual code. And you see the actual code in Akka Streams really represents the graph that we have sketched here. So this is the actual code. The other thing that you see here is the effect of backpressure. Here is the processing URLs per second. You can see when we start, it is really constant. And this is the queue size. This is the backpressure. The beauty of that is that when we write our application, we just express this in the pipeline. You don't need to manually deal with the backpressure. The interesting thing, this is running 10 times faster than the conventional Java application that was implemented with multi-threading. So very cool. So if you need to roll out your own, this is a really good solution. At PayPal, we have a lightweight library called Scoobs, which is addition to Akka Streams, and it is dealing with the large-scale deployment and clusters. We provide support for monitoring, logging, even correlation across services, extra security, and a number of other things. And you can use just the pieces that you need. If you're interested, click on this link, and you'll get a talk from the Reactive Summit. All right, so finally, how are you going to make the choice? Rule number one, you need to create the architectural scenarios for your applications. So that means you need to figure out what are going to be the event sources, what kind of events are you going to send. You also want to know how big are the events, how often are they being sent. You will be sending that into your streaming system. Environment is important because you want to distinguish the behavior of your system where system is fully operational and everything is running fine. Second, when your cluster is degraded, when you start losing machines, when you get slower network. So all of these factors should be considered in your environment. And then you are going to capture what should be the results, what are you going to produce, where do these things go in databases, files, queues, and so on. And you want to figure out what is the rate of results that you need to have. So you need to capture that. And the reason is that we see that various benchmarks of vendors are going to be almost unusable if you have application cases that are different from the benchmark application. And what is really important is I want you to performance test your scenarios, use realistic loads. These days with containers and the cloud, it is easier to achieve that. But you need to have real numbers. So you cannot just believe vendor material that this system is fast. The next thing that you will do, once you have these scenarios and you have measured performance, you want to identify criteria that matter to your project. Some of these criteria are going to be technical. Some of them are non-technical. For example, in some organizations, we have a mandate. We have to use open source. Commercial solutions are not appropriate. You also may want to look into fit to organization, like what are the programming languages in which you are using this. And one of the easy ways to do that is to use the decision matrix, where you will list the criteria that you have. You have weights. I prefer to go just with a simple high, medium, and low. And then for every option, you will evaluate. And it is essential that you have the performance, and you see how this performance actually matches. And don't forget to consider performance for different scenarios in your cluster. So normal operation, degraded. You will see that some of the systems that give you a really good latency, a really good performance, when the machine fails, the system may spend quite a bit of time doing some rebalancing in the cluster. During that time, your system may not be operational. Question is that acceptable? So your scenarios need to consider such failures. So here we are. Based on the criteria that you have, you will choose the winner, hopefully without regrets. And to summarize, different systems have very different runtime characteristics, different developer experience. you need to have architecture aligned with your needs. So don't forget, first create the scenarios. You need to start with that. Performance test your streaming application. Identify technical and non-technical criteria that matter. Evaluate and choose the winner. Questions?
Thank you very much.
And by the way, we are hiring, so you can talk to me after.
Where can we get the slides?
I have uploaded the slides. I think they should be on the website shortly.
Yeah, will all be available from Scale by the Bay pretty soon.
The following question: how do you commonly monitor your streaming systems? Do you use some in-house solutions or probably some open source counterparts? And what is your opinion about how to monitor the streaming system properly? Thank you.
It's an excellent question. So monitoring of streaming systems, or in general any distributed systems, including microservices, is a growing challenge. Normally we see that the systems don't have really good monitoring, and that is why in our organization we are developing, and we have developed a number of custom solutions. There are a couple of interesting innovations in that field. For example, in some organizations you may intentionally insert special kind of messages in order to have a particular traceability. And then you can extract that from your monitoring and representation system. I have seen also some people would generate dot notation, which will then enable them to generate visual graph of how the message passed through the system, which is kind of cool. So there are a number of things. Also, I have seen some organizations providing data for Zipkin. Zipkin will give you the visualization of the flow of data through the cluster, together with some time metrics.
So you had a couple of examples of batch and streaming using the same code. In your experience, so I mean, from your presentation, it's just seamless. You just write code and it works. In your experience, was it so?
Not always. So this is the ideal. This is the ideal. One of the reasons for that is we often see that there are legacy big data applications that are batch. Somebody provided the data, and we had the old days in my old company, we had clients. They would dump file to us once a day. It's a batch process. And then over time, they figure out, well, there is no need to get the results only after 24 hours. Perhaps we could get data immediately. And then we have this code that is doing the business processing. And if we are able to repurpose this code to now work in a streaming fashion, that is a win. And if you consider the applications that we had at that time, which was mostly Spark, we were able to take the business logic, perhaps tweak it a little bit, and get a very similar code for our streaming system. The important thing there was to identify the window of processing and to figure out what is the appropriate semantics. We have seen also at that time that our business logic got complicated in the early days of Spark because we wanted to have the window that corresponds to user session. There was no such mechanism in the beginning, so we had to compensate for that in the business logic. And that changed the similarities between the batch and streaming.
Yes, I'm wondering, are there ways to use workflow management for streaming applications where you can have different streams and you need to have different workflows?
Excellent observation. So could we use workflow management for stream processing? Very attractive idea. And in the past, we have actually done something similar. We have used Apache Camel. But that worked well for situations where our stream of events was really moderate and where we have the message queuing as a source of these events. Normally, the orchestration systems that we have seen could not provide the sufficient support for high volume of data that we see. So in the application that we have done in the Internet of Things space, the volume of data was so big that the workflow system will not work. But what I would love to see is the visualization of the stream processing. And actually, you can see some really nice effort. One of the systems that we have mentioned there was the IBM Streams, which is a commercial system. They have a nice Eclipse-based IDE where you have a graphical composer for your stream processing.
And what the threshold? You say well, there's a limit, and beyond this limit, it's not possible to manage the workflow. So what's this limit?
The limit, it would depend on how you deploy, for example, Apache Camel or some of the other systems. But normally, the workflow systems have been designed to work with conventional messaging and not a very large number of events. What is that number? In our case, the IoT systems were sending us 1.5 million events per second, and we knew that the conventional system just could not handle that.
Okay, we'll have to stop there.
Thank you.